Advanced GraphRAG 2, the next 5 families. Let's dig in. Here is the awkward truth about the memory systems literature. It is a wall of names. Mem0, A-MEM, GMemory, MemGraphRAG, A-MEM. Papers throw them at you as if you already know what they are, and you nod along and learn nothing. We are not doing that here. Each of these 5 gets a proper introduction. What it is, who built it, and the one idea that makes it different before we open the hood on any of them. Before any of it, one piece of hygiene. Of these 5, exactly 2 have cleared peer review. MemGraphRAG at KDD 2026 and A-MEM in Findings of EACL 2026. The other 3, Mem0, A-MEM, and GMemory, are archive preprints. That is not an insult. Preprints are how this field actually moves. It just means the numbers carry different weight, and you want to know which is which before somebody quotes one at you in a design review. First up, Mem0, written MEM0 with a numeral. It comes from the team behind the Mem0 project itself, posted to archive in April 2025, and it ships as both an open source library itself, posted to archive as both an open source library and a hosted service. Here is its one idea, and it is a genuinely different bet from the reference implementation we met last time. A memory is not a triple. A memory is a sentence. Plain, natural language, the kind you could read out loud. Take one line from a conversation. Dana Reyes is now CTO at Helio Systems. The library we met in Part 2E turns that into a typed edge between 2 entity nodes, with date fields hanging off it. Mem0 stores the sentence. That is the entire representation. You lose the ability to traverse, there is no graph to walk, and you gain something real. Anybody on your team can read the store and see exactly what the agent thinks it knows. Mem0 runs in 2 phases, and phase 1 is extraction. Every time a new message pair arrives, it assembles a prompt out of 3 things: a rolling conversation summary, the last 10 messages, and the new pair itself. A model, GPT-4o Mini in their experiments, reads that and returns candidate facts. And note where the summary comes from. It is refreshed asynchronously, off the write path, so summarizing the whole conversation never blocks the thing you are waiting on. Phase 2 is where it gets interesting. Each candidate fact is compared against the 10 most similar memories already on file, and a model is asked, through a function call, so it has to return one of a fixed set, what to do about it. 4 exits: add, update, delete, or no-op. If that shape feels familiar, it should. Part 2D argued that every write is a decision with 4 ways out. This is a vendor putting product names on those exits. Now, the caveat, and it matters. In base Mem0, delete means delete. The memory is removed from the set, gone. But there is a graph variant, Mem0G, built on Neo4j, and it does something different with the same decision. It marks the conflicting edge invalid rather than removing it, and the paper says exactly why: to enable temporal reasoning. 1 product, 2 write policies, and only one of them can answer a question about last quarter. Mem0's evidence comes from a single benchmark, Locomo, scored by a language model acting as judge. Headline: 26% relative improvement over OpenAI's memory feature, 91% lower P95 latency, and over 90% fewer tokens than stuffing the full context. Now read their own table honestly. On open domain questions, ZEP beats them, and plain full context scores the highest judge score anywhere in the paper. Mem0 is faster and cheaper, it is not uniformly better. Second, A-MEM, hyphenated, out of Rutgers University with an independent co-author and the AIOS Foundation, first posted in February 2025. One note on provenance, because we care about this. Its archive listing self-reports a NeurIPS acceptance, but the PDF itself still prints the word preprint on page 1. Unreconciled, so we cite it as a preprint. It's one idea: organize an agent's memory the way a certain German sociologist organized his index cards. Niklas Luhmann wrote something like 70 books, and he gave the credit to a box of index cards. Not a filing system, a Zettelkasten, a slip box, where every card holds one idea, and the value lives in the links between cards, rather than in whatever folder they sit in. There is no schema. There are no categories chosen up front. Structure emerges from what gets connected to what. A-MEM's bet is that an agent's memory should work exactly like that. So what is actually on a card? 7 things. The original content and its timestamp. Those are simply recorded as they arrived. Then 4 the model generates for you: keywords, tags, a 1-sentence contextual description, and an embedding computed over all of that together. And finally, links to other notes. That last field is what makes this a network rather than a list, and it is the field that is going to keep changing long after the note is written. How does a new note find its neighbors? 2 steps, and the split between them is the whole point. First, embeddings produce a shortlist of the nearest existing notes, 40 to 50 of them with the larger models. Then, a language model reads that shortlist and decides which are genuinely related. Embeddings are a cheap filter, not a verdict, which is the same argument Part 2D made about contradiction. Similarity gets you candidates. Judgment gets you the answer. And here is the part with no real equivalent anywhere else in this module. When a new note lands, its neighbors are handed to a model that can decide they should evolve, strengthen, merge, or prune, and it rewrites their context, their keywords, their tags, and their links. The original content and timestamp are never touched. So your old memories are not immutable records. They are drafts that later memories are allowed to edit. Sit with that one for a second. Third, GMemory, from a group spanning the National University of Singapore, Tongji, UCLA, A-Star, and NTU, posted in June 2025 as a preprint, and it is solving a visibly different problem from the first two. Mem0 and A-MEM give one agent a memory. GMemory gives a memory to a whole team of them, several agents talking to each other, working one task together. Its inspiration is not cognitive science. It is organizational memory theory. Why does a team need something different? Because of what a team produces. A single agent leaves a trail. A team of agents leaves a transcript that runs up to 10 times longer in tokens, full of proposals, objections, dead ends, and corrections. Now, compress that down to a final answer and store it. You have kept the conclusion and thrown away the entire collaboration, including, crucially, everything the team learned by getting it wrong the first time. GMemory's answer is 3 graphs stacked on top of one another. At the bottom, the interaction graph, 1 node per utterance, edges recording what was said to whom and what it prompted. In the middle, the query graph, 1 node per past task, carrying its text and whether it ended resolved or failed. At the top, the insight graph, distilled, generalizable lessons, each one pointing back down at the tasks that earned it. When a new query arrives, GMemory walks that stack in both directions. Upward, it asks, what did we learn? Pulling abstract lessons out of the insight graph. Downward, it asks, how did we actually do it? Pulling a condensed slice of the old conversation. And then the clever bit. What each agent receives is rewritten for its role. The planner does not get the coder's lessons. One shared memory, a different parcel for every seat at the table. The headline numbers, attributed properly, up to 20.89% higher success on embodied action, that is MACnet on AlphaWorld, with a Qwen 14B backbone, moving from 58 to 79, and up to 10.12% on Knowledge QA, AutoGen on Hotpot QA, same backbone. Both are gains over having no memory at all, not over a rival memory design. The claim I find more interesting, They got them without changing a line of the host framework. Fourth, and this is the one with a stamp on it, MemGraphRAG from Cheyenne University with a co-author at GLIN, accepted at KDD 2026, camera ready, ACM header, DOI, the lot. And notice something. It is not really an agent memory system at all. It is a graph builder. It takes the word memory and aims it at a completely different target, not the agent's memory of a conversation, but the extractor's memory of the corpus. Its complaint is one you could verify on your own pipeline this afternoon. Standard extraction reads one chunk at a time, in isolation, with no idea what any other chunk said. So chunk 4 calls something an organization. Chunk 90 calls the very same thing a company, and nobody notices. The paper names 3 consequences: thematic irrelevance, logical inconsistency, and structural fragmentation. One graph assembled by a few thousand readers who never once spoke to each other. The fix is not a bigger prompt. It is 3 agents sharing one memory. An extraction agent reads each chunk and writes into that memory. A detection agent scans for conflicts and only reports them. It corrects nothing. A resolution agent settles them using the ontology and the original passage as evidence. And the shared memory has 3 layers: schemas, facts, and the source passages every fact is grounded in. Global context arrives as accumulated state, not as a longer prompt. Here is my favorite mechanism in the paper. A newly extracted schema does not join the graph. It enters what they call a candidate state, pending, stored and counted, but invisible to the global structure. Only once its frequency across the corpus clears a threshold does it flip to stable, and only then do the facts that use it go active. Extraction on probation. And an honest note, the paper never actually tells you what that threshold is. 59.25% average accuracy across 5 datasets, a gain of 2.1 absolute points over the strongest baseline, and that baseline is linear RAG, which you already met in the first course. Retrieval comes back in 61 milliseconds against light RAG's 11 seconds. Their own ablation says the resolution agent matters most, and their own limitations section says the whole thing is text only. Charts and tables have to be transcribed first, and the visual meaning is lost. Fifth and last, A-MEM from INSA Lyon, CNRS, and the Lyris Lab, accepted to findings of EACL 2026. Also a graph builder, but a temporal one, which means that after 5 submodules of groundwork, this is finally a system whose core design is the exact thing we have been building since Part 2A. And its one idea is almost rude in how simple it is. Stop asking the model to do so much at once. Before extracting anything at all, A-MEM shreds the document into atomic facts, snippets that each carry exactly one piece of information. And the splitting rules are where the actual work lives. Compound sentences get split without duplicating anything. Pronouns get replaced with full entity names, so every snippet stands on its own. Relative dates like last week get resolved to absolute ones, and endings, somebody leaving a role, get captured with their own timestamp instead of being dropped. Then, each atomic fact becomes a tiny temporal graph, and here is where you get to feel clever. A-MEM separates observation time, when the system saw the information, from validity time, when the fact actually held. That is Part 2B's 2 clocks, wearing a different jersey. One refinement worth stealing, though? A-MEM stores those timestamps as lists rather than single values, so one edge accumulates the whole history of when a fact started and stopped. Now, put the pieces back together. A-MEM merges pairs of atomic graphs, then merges those results, then merges those. A binary tree collapsing upward, every level running in parallel. And the merge uses no language model at all. Entity matching, relation matching, and unioning the timestamp lists are all done with embeddings and thresholds. The expensive part was the reading. The assembly is arithmetic, which is exactly why the whole thing ends up faster. The expensive part was the reading. The assembly is arithmetic, which is exactly why the whole thing ends up faster. 3 numbers, and they come from 2 different comparisons, so do not let anyone merge them. Around 18 points more exhaustive and 33 points more stable run-to-run. That is against extracting from lead paragraphs without atomic splitting, using the same model. Absolute point gains, not relative ones. The latency cut is a separate comparison entirely, 94% against graffiti. And their own honesty. It costs more in dollars, and it was tested on 1 news corpus. So, 5 introductions done. Now resist the urge to rank them because they are not answering the same question. Mem0 and A-MEM are memory for one agent's conversation. GMemory is memory for a team's collaboration. There are no world facts in it at all. MemGraphRAG builds a better corpus graph and is not temporal. ATOM builds a temporal graph and has no agents. Part 2G takes the axes that actually let you choose and the 2 systems built for trust.
If you like this video, please subscribe and share. Thank you.